Let's go ahead and look at another example of using linear models to make some predictions and also interpret the meaning of the slope and y-intercept within the context of a situation. 4.3, food markup. The scatter plot shows the sales price of several food items and the cost of the ingredients used to produce those items, as well as a line that models the data. The line is also represented by the equation y equals 3.48x plus 0.76. What is the predicted sale price of an item that has ingredients that cost $1.50? Explain or show your reasoning. Okay, so notice on the graph here, we have a x-axis, which has ingredient cost in dollars, and then the y-axis over here, that is sales price in dollars. So the first statement here talks about ingredients that cost $1.50, and the ingredients cost is the x value. So $1.50 is the x value. So let's go over and find $1.50 on the x-axis. Let's then follow it up to the linear model and see what it then predicts for the ingredients cost. So we notice that that point right there, that would have $1.50 as the ingredients cost, would have $6 for the sales price. Notice it's not one of the black points, it's not a scatter plot point, but it is a point that is on our estimated linear model line, and that's what we're using to make the prediction. So our estimate from the graph, we'll say from linear model, graph, is $6. That's what that would translate to if we started with an ingredients cost of $1.50. All right, we could also use the equation to work that out as well. So if we wanted to use the equation, we could get even a more precise estimate. Now we are given the equation. So let's go ahead and take the equation. And again, since we have the x value of $1.50, we'll put that in for x in our equation. And I'm talking about this equation right up here that we're given. And let's just run the calculations on that. So if we take and go 3.48 times $1.50, so 1.50 plus 0.76, that comes out to 5.98. So $5.98. Now that's just a little bit more precise, isn't it? So that comes out to $5.98. So I'm just going to see if I can fit that on here. So what that really means is that this point right here is not exactly at 6. It's actually 5.98. So if we wanted to now use that one, that's actually what this point right here is. It just looked from the graph like it was right on 6, but it's just below it, and that's what the equation helps us see. All right, so the equation estimate is probably a little bit more precise, but certainly just looking at the line gives us a pretty good estimate as well. All right, number 2. What is the predicted ingredient cost of an item that has a sales price of $7? Explain or show your reasoning. So this time, notice it's a sale price of the, what is the predicted ingredient cost? Okay, so that's what we're trying to find, that has the sales price of $7. So notice this time we're starting with the sales price of $7. And so if you want to kind of do an estimate from the graph here, then we would follow it over to the line until it hits that line and then down. All right, so that's going to be a little bit harder to estimate. We'll just do our best we can. So that looks like it's, I don't know, right in the middle between 1.5 and 2 here on the x-axis. So maybe 1.75. All right, so let's write that down. So estimate from linear model is about 1.75, so $1.75 for the ingredient cost. So notice we worked backwards on that one because we were given the Y value and we had to go over to the line and down to figure out the X value. But just like we did in problem number 1, let's see if we can get an even more precise estimate by actually using the equation. So let's use the equation. Now notice that we're given the Y value, the sales price is on the Y-axis. So if we are plugging this into the equation, we're going to have to put it in for Y. So put the 7 in for Y. And we'll actually have to work backwards and figure out what the X value is. So this will actually require us to solve the equation. And so this is just like what we've been doing all year long, just kind of working backwards and solving. So to get X by itself, let's undo the 0.76 by subtracting it from both sides. So that cancels that out. And 7 minus 0.76 gives us 6.24. 6.24 equals 3.48x. And just like we've done before, 3.48 times x. So to undo multiplication to get x by itself, we'll divide both sides by 3.48. And then that should give us our x. Let's see how close we were to $1.75 here. So 6.24 divided by 3.48. Okay, so $1.79, so 1.793. So yeah, pretty close there. So that gives us about $1.79. So that's really what this is right here, where it hits the, in other words, the coordinates of that point right there would be 1.79 and 7. So that's $1.79. So it looked like it was about $1.75, but it was really hard to tell exactly what that was on the scale. But the equation dialed that in for us. So now we have a really more precise estimate. So working our way backwards there. All right, number 3. What is the slope of the linear model and what does that mean in the situation? All right, well, we already know the linear model equation right here. And when we think about y equals mx plus b, that number, that coefficient in front of the x is our slope. So we know 3.48 is our slope just by looking at the equation. And recall the slope is the change in y divided by the change in x, and that slope literally will mean the change in the y value for every 1x. So on the x-axis, we have ingredient costs. So for every $1 increase in ingredient cost, the sales price increases by $3.48. Okay, so once again, the slope, when it's written as a number in front of x, is going to be how much the y changes for every 1x. So every time we go over 1 on the x-axis, it tells us how much the y value is changing. So in this case, the ingredients cost is on the x-axis. So for every $1 increase in ingredients costs, the price is increasing, our line is going up, so our price is increasing by 3.48. All right, what does the y-intercept of the linear model? What is the y-intercept? What does it mean in this situation? Does this make sense? All right, so the slope made some sense. Let's see what the y-intercept would be. So the y-intercept, remember when it's in y equals mx plus b form, is the number that's kind of hanging out over on its own here. So just by looking at the equation, we know the y-intercept is 0.76. It kind of looks like that here, by the way. It's tough to tell exactly what that is just by looking at the graph, but it crosses the y-axis at 0.76, 0, comma 0.76. So think about that. That means that there's an ingredients cost of 0, and then the sales price would then be 0.76. So if the ingredients cost $0, because that would be the coordinates of the y-intercept. Remember, y-intercept is 0, comma 0.76. So if the ingredients cost are $0, then the sales price would be 76 cents. So does that make sense? Does that make sense in our situation that if there's no cost to ingredients for the food item, that it would still be set at a sales price of 76 cents? Okay, well, I mean, you can interpret this a couple different ways. Maybe we say possibly yes, that makes sense. Because maybe there is a startup cost of some sort. Maybe there's some background cost for setting up the thing that you were going to sell. Maybe there's container cost. Maybe you had to buy some containers. Maybe there's some background cost. So maybe 0.76 is like the startup cost per item. So you could interpret it that way. Or maybe you say, possibly no, that doesn't really make sense. Right? If the ingredients cost $0, then why would the food cost 76 cents? Then why would there be any sales price of 76 cents? Okay, so there's a little bit of interpretation on this particular problem with the y-intercept value. And so that's all right. As long as you explain yourself and kind of what you're thinking on that, and that explanation fits the context of the problem,